Picture this, the universe, just moments after its birth, trembling like a spider's web caught in a cosmic breeze. These faint shivers, space-time ripples from the dawn of everything, might still echo around us today, hidden in the fabric of reality. What if I told you these ancient whispers could rewrite the story of how our universe began? From colliding bubble universes to black holes older than time itself, scientists have uncovered 30 mind-bending theories about these primordial gravitational waves. Some sound like science fiction, others border on the unbelievable, but each one could hold the key to unlocking the universe's deepest secrets. Strap in, because we're about to dive into the wildest cosmic detective story ever told. By the end of this journey, you'll never look at the night sky the same way again. Ready to unravel the mystery? Let's begin. Now let's zoom in on the very first theory, one that reshaped how we think about the universe's earliest moments. Alan Gough's groundbreaking idea, known as inflationary cosmology, suggests that the universe didn't just expand after the Big Bang. It exploded outward at an unimaginable speed, stretching faster than light itself in a fraction of a second. This hyper-fast expansion, called inflation, didn't just smooth out the cosmos, it also left behind faint tremors in space-time. Here's how it works. Tiny quantum fluctuations, those random jitters at the smallest scales, got stretched along with the universe during inflation. What started as microscopic ripples became colossal waves, frozen into the fabric of reality as gravitational echoes. Today, scientists hunt for these ancient ripples with tools like advanced telescopes and gravitational wave detectors, hoping to catch a whisper of that explosive moment. If they succeed, it wouldn't just confirm Gough's theory, it would give us a direct snapshot of the universe's first trillionth of a second. Imagine that, decoding the birth of everything from vibrations older than stars. Now, let's take a step into the bizarre and mind-bending world of the quantum foam hypothesis. Picture space-time not as a smooth, unbroken fabric, but as a seething, frothy ocean at the tiniest scales imaginable. This theory suggests that space itself is constantly bubbling with tiny fluctuations, like a pot of water just before it boils. These aren't just random blips, they're ripples woven into the very fabric of reality, a fundamental property of the universe itself. Stephen Hawking was one of the giants who explored this idea, showing how these quantum jitters could challenge everything classical physics taught us about space and time. Instead of a predictable, orderly cosmos, we might be living in a universe where space-time is inherently chaotic at its core. These fleeting bubbles of energy pop in and out of existence so quickly that we can't see them directly, but their effects could leave traces in gravitational waves. If this hypothesis holds, it means the ripples we detect today might not just be leftovers from the Big Bang. They could be the ongoing hum of space-time itself, vibrating like the strings of a cosmic instrument. It's a radical shift from the smooth, unchanging universe Einstein once imagined, and it opens up a whole new way to think about gravity, quantum mechanics, and the true nature of reality. Now, let's stretch our imaginations even further with another fascinating possibility: cosmic string vibrations. Imagine the universe not long after the Big Bang, a time when reality was still settling into its current form. Among the chaos, thin, incredibly dense strands of energy might have formed, stretching across the cosmos like invisible guitar strings. These are cosmic strings, hypothetical one-dimensional objects, remnants of the early universe's violent birth. Unlike anything we see today, these strings would be under immense tension, vibrating at incredible speeds. Every wiggle, every twist could send ripples through space-time itself, creating gravitational waves that might still echo across the universe. What's wild is that these strings wouldn't just fade away. If they exist, they could still be out there, humming faintly in the darkness, waiting to be detected. Modern observatories like LIGO and future detectors might one day pick up these signals. the patterns they'd find wouldn't match black hole mergers or neutron star collisions. They'd be something entirely new, a direct whisper from the universe's earliest moments. It's a thrilling thought that these cosmic relics could be hiding in plain sight, their vibrations carrying secrets about how everything began. And if we find them, it wouldn't just confirm a wild theory, it would rewrite our understanding of the cosmos. Now, let's take a step into one of the most mind-bending ideas out there, the possibility that our universe isn't alone. Picture this, floating in some vast, higher-dimensional space. Our universe might be just one bubble among countless others, each with its own laws of physics. And sometimes these bubbles collide. When two of these bubble universes smash together, the impact could send shockwaves rippling through space-time, leaving behind gravitational waves as cosmic fingerprints. Think of it like two soap bubbles merging, except instead of soapy water, its entire universes crashing in dimensions we can't even see. Physicists like Leonard Susskind have explored this wild idea, suggesting that these collisions could have happened in the earliest moments of existence, imprinting their energy onto the fabric of reality itself. The crazy part, if we detect these ripples, it wouldn't just prove that gravitational waves existed, could be our first real evidence of other universes. Imagine that, a signal from beyond our cosmic bubble, telling us we're not alone in the multiverse. And while it sounds like science fiction, some of the brightest minds in physics take it seriously, working on theories that might one day turn this speculation into fact. So keep an eye on those detectors, because the next big discovery might not just reshape our universe, but reveal an entire cosmic neighborhood we never knew was there. Now let's shift our gaze to another cosmic heavyweight: black holes. But not just any black holes. We're talking about primordial black holes, ones that could have formed mere seconds after the Big Bang, when the universe was a seething, dense soup of energy. These ancient monsters, born from the chaos of the early cosmos, might hold the key to some of the first ripples in space-time. Picture this: in those first frantic moments, pockets of ultra-dense matter could have collapsed under their own gravity, forming black holes far smaller than the ones we see today, some no bigger than an atom, yet packing the mass of a mountain. And when these tiny titans collided and merged, the violence of those crashes would have sent gravitational waves surging through the infant universe, like ripples from a stone tossed into a pond. Here's where it gets even more fascinating. The LIGO Observatory, which made history by detecting gravitational waves in 2015, might have already picked up echoes of these primordial mergers. Some scientists speculate that certain signals LIGO has captured could belong to black holes that aren't just old, but ancient relics from the universe's first breath. If true, it would mean we're not just hearing the groans of modern black holes, but whispers from the dawn of time itself. What's at stake? If primordial black holes really did merge in the early universe, their gravitational waves could help us solve one of astronomy's biggest mysteries: dark matter. Some theories suggest these tiny black holes might actually be dark matter, lurking unseen but shaping the cosmos with their gravity. So every ripple we detect could be a clue, not just to the universe's birth, but to the invisible scaffolding that holds it together. The hunt is on. With each new detection, we're peeling back layers of cosmic history, listening for the faintest tremors that might rewrite our understanding of everything. And who knows, the next signal could be the one that changes it all. Now, let's dive into a different kind of cosmic drama, one where the very fabric of reality itself undergoes a radical transformation. Picture the early universe not just as a hot, dense soup, but as a place where the rules of physics were still being written. Back then, the fundamental forces we know today, like gravity, electromagnetism, and the nuclear forces, were all tangled together in a single, unified superforce. But as the universe expanded and cooled, it went through a series of phase transitions, like water freezing into ice, except on a cosmic scale. One of the most dramatic of these shifts happened when the electroweak force split into two: electromagnetism and the weak nuclear force. This wasn't just a quiet change, it was a violent upheaval, releasing enormous amounts of energy as the universe's structure rearranged itself. And just like a pot of boiling water sends bubbles rippling to the surface, these phase transitions could have sent shockwaves through space-time, creating gravitational waves that might still echo across the cosmos today. But here's where things get even wilder. Some theories suggest the universe might not have settled into its current state permanently. There's a concept called false vacuum decay, which imagines our universe as a bubble in a higher energy, false state, one that could, at any moment, collapse into a more stable configuration. If that happened, the boundary between the old and new phases would race outward at the speed of light, releasing a tsunami of energy that would rewrite the laws of physics in its wake. And yes, that cataclysmic event would send gravitational waves rippling through the cosmos like a cosmic alarm bell. What's incredible is that these waves could carry clues about the universe's most fundamental symmetries, the hidden rules that govern everything from particles to galaxies. Future detectors like the proposed laser interferometer space antenna might one day pick up these faint tremors, giving us a front-row seat to the universe's most transformative moments. So every time we listen for gravitational waves, we're not just hearing black holes collide. We might be eavesdropping on the universe as it grows up. Now, let's step into a universe where the Big Bang isn't the beginning. It's just another chapter in an endless cosmic cycle. This is the ekpyrotic universe model, a radical alternative to inflation that imagines our universe as a four-dimensional brain floating in a higher dimensional space. Picture two of these brains like giant sheets drifting toward each other until, bang, they collide. That collision isn't just a one-time event. It's the engine of a cyclic universe where every crash sparks a new Big Bang followed by expansion, cooling, and eventually another collision over and over again. What's fascinating here is how these brain collisions could generate gravitational waves. Unlike inflation's quantum fluctuations, these ripples come from the sheer violence of the collision itself, like the shock waves from two ocean waves crashing together. And because the process repeats, these waves might carry a unique fingerprint, a pattern that future detectors could potentially spot. Paul Steinhardt, one of the architects of this theory, saw it as a way to solve some of inflation's puzzles. For instance, why does our universe look so uniform? Inflation says it's because of rapid expansion, but the ekpyrotic model suggests it's because the brains were nearly parallel and smooth before colliding. No need for a mysterious inflated field, just gravity and extra dimensions doing the work. Of course, this idea isn't without its critics. Some argue that brain collisions would leave the universe too lumpy or that the math doesn't quite add up. But that's the beauty of cosmology. Every bold idea pushes us to test, debate, and refine our understanding. Whether the ekpyrotic model holds up or not, it reminds us that the universe's first ripples might not just be echoes of a single birth, but part of an infinite cosmic rhythm. And if we're lucky, the next generation of gravitational wave detectors might just catch the beat. Now, let's take a step into a universe where reality might not be what it seems. Imagine space-time not as a solid, three-dimensional stage, but as a hologram, a two-dimensional surface projecting all the richness of our three-dimensional world. This is the holographic principle, a mind-bending idea that suggests the universe's information is encoded on its boundary, like a cosmic DVD storing everything we see and experience. So how does this connect to gravitational waves? If space-time is truly a projection, then ripples in it, gravitational waves, might carry hidden clues about the deeper, lower-dimensional reality. Think of it like waves on the surface of a pond. The patterns they create could hint at something happening beneath, in this case, the quantum gravity laws governing the universe's true structure. This idea ties closely to something called the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. It's a mathematical framework that suggests a holographic universe with gravity in higher dimensions can be perfectly described by a quantum theory without gravity on its boundary. In simpler terms, the messy quantum interactions at the edge could encode the smooth gravitational waves we detect. If this holds true, future gravitational wave observatories might not just be listening to the echoes of black hole mergers or cosmic collisions. They could be decoding the universe's holographic blueprint, revealing secrets about quantum gravity that have eluded us for decades. Skeptics argue that testing this is a monumental challenge, but if the holographic principle is right, the universe's first ripples might be more than just vibrations in space-time. They could be messages from the edge of reality itself. Now let's turn our attention to one of the universe's greatest mysteries, dark matter. We can't see it, we can't touch it, yet it makes up roughly 85% of all matter in the cosmos. But what if this invisible stuff didn't just shape galaxies? What if it also left ripples in space-time itself? Here's the idea. In the early universe, dark matter particles might have collided or decayed, releasing bursts of energy. These violent interactions could have sent gravitational waves rippling through the fabric of space-time, like stones dropped into a pond. Unlike the waves from black hole mergers we detect today, these would be far older and fainter echoes from a time when the universe was just taking shape. The challenge: detecting them. Current observatories like LIGO aren't sensitive enough to catch these primordial whispers, but future projects like the Laser Interferometer Space Antenna, or LISA, could change that. This space-based detector, set to launch in the 2030s, will hunt for low-frequency gravitational waves, the kind that might carry signatures of dark matter's early dance. Some theories even suggest that dark matter isn't just one type of particle, but a whole hidden sector with its own forces and interactions. If that's true, the gravitational waves from these exotic processes could reveal entirely new physics, rewriting our understanding of the cosmos. Skeptics point out that dark matter's nature is still unknown, making this a high-stakes gamble. But if we're right, the universe's first ripples might hold the key to unlocking its darkest secret. Now, let's shift our gaze to another ghostly player in the cosmic drama: neutrinos. These tiny, nearly massless particles are everywhere, streaming through you right now at nearly the speed of light. But in the early universe, they weren't just passive spectators. They might have been cosmic agitators, stirring up space-time itself. Picture this: moments after the Big Bang, the universe was so dense and hot that neutrinos, usually aloof and barely interacting, were packed together like commuters in a rush-hour subway. Their sheer numbers and chaotic motion could have created turbulent flows, like a stormy ocean on a galactic scale. These swirling currents would have tugged at the fabric of space-time, leaving behind faint gravitational ripples. Here's where it gets even wilder. Neutrinos are shape-shifters, oscillating between different types as they travel. In the early universe, this quantum dance could have amplified their turbulence, making their gravitational fingerprints more pronounced. Today, detectors like IceCube in Antarctica and Super Kamiok and in Japan study neutrinos from distant supernova, but catching traces of their primordial chaos. That's a taller order. Future experiments like the proposed cosmic neutrino background detector aim to listen for these ancient whispers. If they succeed, we might decode a hidden chapter of the universe's infancy, one written not in light or matter, but in the restless flutter of neutrinos. Skeptics argue that their signals would be drowned out by other cosmic noise. But if neutrinos did leave their mark, it would rewrite our understanding of how the universe's first ripples came to be. Now let's step into the realm of supersymmetry, a theory that could unlock some of the universe's deepest secrets. Supersymmetry, often called SUSY for short, proposes that every particle we know has a hidden superpartner, a heavier, more exotic twin. These superpartners aren't just theoretical curiosities. In the early universe, they might have played a crucial role in shaping the first ripples in space-time. Imagine the cosmos just moments after the Big Bang, teeming with these superparticles. As the universe expanded and cooled, many of them would have decayed into lighter particles, releasing bursts of energy in the process. These violent decays could have sent shockwaves through space-time, leaving behind faint gravitational imprints. If we could detect those echoes today, they'd give us a direct window into physics far beyond what our current experiments can reach. That's where CERN comes in. The Large Hadron Collider has spent years hunting for signs of supersymmetry, smashing particles together at unimaginable speeds to see if any superpartners emerge. So far, the search has turned up empty, but that hasn't dampened the excitement. SUSY remains one of the most compelling ideas in physics because it could solve multiple puzzles at once, from the nature of dark matter to the hierarchy problem, which asks why gravity is so weak compared to other forces. If supersymmetry is real, the gravitational waves from those early superpartner decays might still be out there, waiting to be discovered by next-generation detectors. It's a long shot, but if we find them, it wouldn't just confirm SUSY, it would rewrite the story of how the universe's first ripples came to be. Skeptics argue that supersymmetry might be too elegant to be true, but in a cosmos full of surprises, who's to say these hidden waves aren't just waiting to be uncovered? Now, let's turn our attention to another fascinating possibility: action field oscillations. These hypothetical particles might sound like something out of science fiction, but they could hold the key to unraveling two of the universe's biggest mysteries: dark matter and the strong CP problem. Actions are thought to be incredibly light, ghostly particles that emerged as the universe cooled after the Big Bang. Unlike ordinary matter, they don't interact much with light or other particles, making them nearly invisible. But here's where things get interesting. As the cosmos expanded and temperatures dropped, these action fields would have started oscillating like waves rippling across a pond. Those oscillations could have subtly warped space-time itself, leaving behind faint gravitational imprints, ripples that might still linger today. What makes actions especially compelling is their dual role in physics. On one hand, they could solve the strong CP problem, a puzzle about why certain subatomic interactions don't behave the way we'd expect. On the other, they're a leading candidate for dark matter, the invisible stuff that makes up most of the universe's mass. If actions exist, their gravitational wave signatures could be hiding in the noise of the cosmos, waiting for ultra-sensitive detectors to pick them up. Scientists are already hunting for these elusive particles using experiments like ADMX, which scans for faint action signals in magnetic fields. If they succeed, it wouldn't just confirm a new particle, it would give us a whole new way to probe the universe's earliest moments. The idea that something as subtle as action oscillations could have shaped the fabric of space-time is a reminder of how even the smallest players in physics might leave the biggest marks. Now, shifting gears to a radically different perspective, let's dive into loop quantum gravity's take on space-time ripples. Unlike the smooth, continuous fabric of space-time we're used to imagining, this theory suggests reality might be stitched together from tiny, discrete loops. Think of it like pixels on a screen, but for the universe itself. These loops, woven into a network, could vibrate or snap under extreme conditions, sending out gravitational waves with a signature unlike anything predicted by classical physics. What sets loop quantum gravity apart is its refusal to blend gravity with other forces. Unlike string theory's quest for a unified framework, instead, it reimagines space-time's very structure, proposing that at the smallest scales, gravity's quantum nature becomes undeniable. If this theory holds, the earliest moments of the cosmos wouldn't have been a singularity but a quantum bounce, a rebound from a previous universe's collapse. That bounce could have sent shockwaves through space-time, leaving ripples with a telltale pattern, jagged, uneven, and full of quantum fingerprints. Compare this to string theory, where gravitational waves emerge from vibrating strings in extra dimensions, a symphony of higher dimensional harmonics. Loop quantum gravity, by contrast, is more like a cosmic drumbeat, its rhythms dictated by the granularity of space itself. While both theories aim to reconcile Einstein's gravity with quantum mechanics, their predictions for primordial ripples couldn't be more distinct. The challenge: detecting these differences. Current observatories like LIGO aren't sensitive enough to spot the quantum texture loop gravity predicts. But future missions, like the proposed Big Bang Observer, might just have the precision to catch these whispers from the universe's first moments. Whether space-time is smooth or pixelated, one thing's certain: the answer would rewrite physics as we know it. Now, let's venture into one of the most mind-bending ideas yet: white holes. Imagine a black hole, but in reverse. While black holes suck everything in, never letting even light escape, white holes would theoretically blast matter and energy outward, like a cosmic fountain erupting from nowhere. These bizarre objects are purely hypothetical for now, but if they existed in the early universe, their violent explosions could have sent shockwaves through space-time, leaving behind unique gravitational ripples. The math behind white holes comes straight from Einstein's equations. They're essentially black holes played backward in time. But here's the catch: while black holes form naturally from collapsing stars, white holes would require some exotic physics to exist. Some theories suggest they could be the other end of a wormhole, or even the remnants of a universe that collapsed and rebounded, spewing out everything it once swallowed. Detecting white hole signatures would be like finding a needle in a cosmic haystack. Their eruptions would be incredibly brief and rare, making them far harder to spot than black hole mergers. But if we ever caught one, the gravitational waves would look nothing like what LIGO or Virgo usually detect. Instead of the classic chirp of colliding black holes, we might see a sharp, explosive burst, a single, dramatic spike in the data. Critics argue white holes are more science fiction than science, since they'd violate the second law of thermodynamics by seemingly creating energy out of nowhere. Yet, in the chaos of the early universe, where the rules of physics were still being written, who's to say they couldn't have flared into existence even briefly? Whether real or just a mathematical curiosity, white holes remind us that the universe's first moments might have been stranger than we dare to imagine. Now, let's stretch our imaginations even further into the realm of extra dimensions. Picture our familiar four-dimensional universe with its 3 dimensions of space and 1 of time. But what if there were more dimensions curled up so tiny we can't perceive them? This is the heart of the Kaluza-Klein theory, a bold idea that suggests gravitons, the hypothetical particles carrying gravity, could leak from these hidden dimensions, creating ripples in space-time. Here's how it works. In string theory, these extra dimensions are compactified, meaning they're folded into incredibly small scales. But occasionally, gravitons might escape, vibrating through our observable universe like echoes from a higher dimensional world. These escaping gravitons would carry energy, and as they move, they could generate faint gravitational waves, signatures of dimensions beyond our own. String theory provides the framework for this idea, proposing that the universe operates in 10 or even 11 dimensions. The Kaluza-Klein gravitons are like messengers from this grander cosmic architecture, hinting at a reality far more complex than we can see. If detected, their waves would offer a direct window into these hidden dimensions, revolutionizing our understanding of gravity itself. Of course, the challenge is immense. These ripples would be extraordinarily subtle, drowned out by the noise of more conventional gravitational wave sources. But future detectors with unprecedented sensitivity might just catch a whisper of these higher dimensional vibrations. Whether Kaluza-Klein gravitons are real or not, they remind us that the universe's deepest secrets might lie in the spaces we can't even see. Now, let's turn our attention to something even more mind-bending: the idea that empty space isn't really empty at all. According to quantum mechanics, the vacuum of space is a seething sea of tiny, fleeting fluctuations. Particles and antiparticles pop in and out of existence so quickly we can't see them, but their effects are very real. These quantum jitters, stretched by the rapid expansion of the early universe, might have grown into the first ripples in space-time. Here's the fascinating part. The uncertainty principle tells us that on the smallest scales, energy can't be perfectly still. Even in a vacuum, there's always a tiny bit of chaos. In the moments after the Big Bang, as the universe expanded at an incredible rate, these microscopic fluctuations could have been stretched across vast distances. What started as a tiny quantum wobble might have been amplified into a full-fledged gravitational wave, leaving an imprint we could detect today. Think of it like ripples on a pond. If you disturb the water gently, you get small waves. But if the pond suddenly expands to the size of an ocean, those tiny ripples grow into massive swells. In the same way, the universe's explosive growth could have turned quantum noise into cosmic echoes. The challenge, of course, is finding these ancient ripples. They'd be incredibly faint, buried under the noise of more recent events like black hole collisions. But if we could detect them, they'd give us a direct glimpse into the quantum nature of the universe's birth. It's a reminder that even the emptiest corners of space hold secrets, and those secrets might still be whispering to us across billions of years. Now, let's take a step into the realm of cosmic shortcuts, wormholes. These hypothetical tunnels through space-time, often called Einstein-Rosen bridges, might have played a wild role in the early universe. Picture this: tiny primordial wormholes formed in the chaos just after the Big Bang, colliding or even evaporating. The energy released from these events could have sent powerful ripples through space-time, leaving behind gravitational echoes we might detect today. Einstein's theory of general relativity allows for the existence of wormholes, though they'd require exotic matter to stay open. In the extreme conditions of the early universe, these structures could have been more common, popping in and out of existence like quantum bubbles. If two wormholes collided or one suddenly collapsed, the energy released would have been immense, enough to create gravitational waves that could still be faintly traveling through the cosmos. This idea ties directly into the Einstein-Rosen bridge concept, where a wormhole acts as a shortcut between 2 points in space-time. While we usually think of wormholes as stable, traversable tunnels, the early universe might have been filled with unstable, fleeting versions. Their violent endings, whether through collisions or evaporation, could have been a significant source of those first space-time ripples. Detecting these ancient signals would be like finding a cosmic fingerprint of wormholes. It wouldn't just confirm their existence, it would tell us they were active players in the universe's infancy. And if that's true, it opens up even wilder questions. Could some of these wormholes have survived? Are they still out there, hidden in the fabric of reality? For now, it's a tantalizing mystery, but one that future gravitational wave detectors might help us solve. Now, shifting our gaze to one of the universe's most mysterious forces, dark energy. We often think of it as the invisible hand pushing the cosmos apart at an accelerating rate today. But what if it wasn't always this way? Some theories suggest dark energy might have behaved very differently in the early universe, leaving behind faint gravitational ripples as a clue. Imagine dark energy wasn't constant but evolved over time like a cosmic chameleon. This idea is at the heart of quintessence models, where dark energy isn't just a static force but a dynamic field that changes. In the universe's first moments, this field could have fluctuated wildly, releasing bursts of energy that warped space-time. Those distortions might still linger today as subtle gravitational waves waiting to be detected. What makes this theory so intriguing is how it flips our understanding. Instead of dark energy being a steady background player, it could have been an active shaper of the early cosmos. If those ripples are found, they'd give us a snapshot of how dark energy operated when the universe was young, whether it was stronger, weaker, or even interacted with other forces in ways we can't yet imagine. And here's the kicker: if dark energy wasn't constant, it could mean the fate of the universe isn't set in stone. Maybe the acceleration we see today is just a phase, and dark energy will shift again. Unraveling these ripples wouldn't just rewrite the story of the past, it could change how we see the future. For now, it's a puzzle wrapped in the fabric of space-time, but one that future observatories might finally piece together. Now, let's take a step into the mind-bending realm of loop quantum cosmology, where the universe might not have begun with a bang, but a bounce. Picture this: instead of a singular explosion, our cosmos could have been born from the collapse of a previous universe, rebounding like a cosmic phoenix. This is the heart of the Planck star theory, where the universe's death isn't an end but a transformation. At the moment of this quantum bounce, the universe would have been compressed into an unimaginably dense object, a Planck star. Think of it as a black hole's theoretical opposite, where gravity's crush hits a limit and space-time snaps back, sending shockwaves rippling outward. These echoes wouldn't just be ordinary gravitational waves. They'd carry the fingerprints of the universe's rebirth, encoded in their unique frequencies. What's fascinating is how this idea challenges the traditional Big Bang narrative. If Planck stars exist, their gravitational wave echoes could be the smoking gun for a cyclical universe, one that has lived, died, and been reborn countless times. Future detectors might one day catch these whispers from the past, revealing whether our cosmos is part of an endless cycle of collapse and renewal. And here's the twist: these echoes wouldn't just tell us about the universe's origins. They could also hint at the nature of quantum gravity itself, bridging the gap between Einstein's relativity and the quantum world. For now, it's a theory wrapped in mystery, but one that turns the universe's greatest catastrophe into its most creative act. Now, let's shift gears to a theory that sounds like it's straight out of a cosmic detective story: magnetic monopoles. These elusive particles, predicted by grand unified theories, are like the universe's missing puzzle pieces. Unlike ordinary magnets, which always come with both a north and south pole, magnetic monopoles would carry just one, a single magnetic charge. The idea was first proposed by physicist Paul Dirac back in the 1930s, and if they exist, they could rewrite our understanding of the early universe. Here's where it gets wild. In the extreme heat of the cosmos' infancy, these monopoles would have been incredibly abundant. But as the universe cooled, they might have started annihilating each other in violent bursts of energy. Picture two cosmic opposites colliding and vanishing in a flash, sending shockwaves through the fabric of space-time itself. These ripples wouldn't just be random noise, they'd carry clues about the universe's earliest moments, like echoes of a long-lost battle between matter and antimatter. What makes this theory so compelling is its connection to cosmic relics. If monopoles were real, their remnants could still be lurking in the universe today, hidden in the vast emptiness between galaxies. And if we ever detect their gravitational wave signatures, it wouldn't just confirm Dirac's bold prediction, it could also reveal how the fundamental forces of nature split apart in the universe's first split seconds. So while magnetic monopoles remain hypothetical for now, they're a tantalizing piece of the cosmic puzzle. Whether they're out there or not, their story reminds us that the universe's deepest secrets might be written in the ripples we're only just learning to read. Now, let's take a step into the unpredictable with a theory that turns cosmic order on its head: chaotic inflation. Proposed by physicist Andre Linde, this idea suggests that the early universe wasn't just expanding smoothly, but in a wild, almost random dance. Imagine space-time as a bubbling pot with different regions inflating at different rates due to tiny quantum jumps. These fluctuations weren't just minor blips, they could have created a patchwork of ripple patterns across the cosmos, each telling its own story of how space-time stretched and twisted. What makes chaotic inflation so fascinating is its sheer variety. Unlike traditional inflation models, which assume a uniform process, Linde's version embraces the chaos. Picture a cosmic kaleidoscope where every twist and turn generates new gravitational wave signatures. Some regions might have stretched faster, others slower, leaving behind a rich tapestry of ripples that could still be detectable today. This isn't just about randomness, it's about how the universe might have used chaos to create the structure we see now. The real kicker, chaotic inflation, opens the door to the multiverse. If different pockets of space-time inflated in wildly different ways, we might be living in just one of countless universes, each with its own unique ripple patterns. It's a humbling thought our entire cosmos could be a single note in a grand cosmic symphony. And if future experiments catch these ripples, they might not just reveal our universe's past, but hint at the infinite possibilities beyond it. So while chaotic inflation might sound like cosmic anarchy, it's actually a brilliant twist on how order can emerge from randomness. Whether it's the true story of our universe or just one piece of the puzzle, it reminds us that sometimes the most beautiful patterns come from the most unexpected dances. Now, let's shift our gaze to a concept that bridges the fiery birth of the universe with the delicate threads of string theory, the Hage-Dawn phase transition. Picture the early cosmos not as a smooth, cooling soup, but as a seething cauldron of energy so intense that matter itself behaved in bizarre, unpredictable ways. This is where the Hage-Dawn temperature comes into play, a critical threshold named after physicist Rolf Hage-Dawn, who theorized that at this extreme heat, the very nature of particles would undergo a radical transformation. In string theory, the Hage-Dawn temperature marks the point where traditional particles can no longer exist as we know them. Instead, they unravel into vibrating strings, the fundamental building blocks of reality in this framework. Think of it like heating ice until it melts into water, but on a cosmic scale, except here, particles dissolve into a chaotic tangle of strings. This phase transition wouldn't have been quiet. The sudden shift could have sent violent tremors through space-time, generating gravitational waves that might still echo across the universe today. What's truly mind-bending is how this idea connects to the larger puzzle of the cosmos. If the early universe did hit the Hage-Dawn temperature, it wouldn't just be a footnote in physics. It could explain why we see certain patterns in the cosmic microwave background, or why gravitational wave detectors pick up faint, ancient signals. String theory often feels abstract, but this phase transition grounds it in something tangible, a moment of cosmic upheaval that left ripples in its wake. So while the Hage-Dawn temperature might sound like an obscure detail, it's a thrilling reminder that the universe's infancy was anything but calm. Whether these ripples are waiting to be discovered or lost to time, they offer a glimpse into a time when the fabric of reality itself was rewriting the rules. And who knows, the next big breakthrough in gravitational wave astronomy might just trace back to this explosive chapter in cosmic history. Now, let's step into a realm where even the rules of geometry get a cosmic twist: non-commutative space-time. Imagine a universe where the order in which things happen isn't just important, it's fundamental to how reality works. In ordinary math, 2 times 3 is the same as 3 times 2. But in non-commutative geometry, swapping those numbers could give you a completely different result. This isn't just a quirky math puzzle. It's a radical rethinking of space-time itself, pioneered by mathematician Elaine Kahn. Here's how it connects to gravitational waves. If space-time at its smallest scales doesn't follow the usual rules of geometry, its structure could be constantly shifting in tiny, unpredictable ways. These fluctuations wouldn't just be random noise, they might generate faint ripples in the fabric of the universe, like waves lapping against a shore we can't yet see. Elaine Kahn's work suggests that these ripples could carry a unique signature, one that's fundamentally different from the waves predicted by classical physics or even string theory. What makes this idea so compelling is how it challenges our assumptions. We're used to thinking of space as smooth and continuous, but non-commutative geometry paints a picture where even the act of measuring distances could create tiny disturbances. If detectors like LIGO or future observatories ever pick up gravitational waves that don't match any known model, non-commutative geometry might be the key to decoding them. So while this theory might sound abstract, it's a reminder that the universe's first moments could have been governed by rules we're only beginning to grasp. Whether these ripples are out there waiting to be found or lost in the noise of cosmic history, they offer a tantalizing clue that the birth of space-time might have been far stranger than we ever imagined. Now, let's turn our attention to something truly mind-bending: black hole superradiance. Picture a spinning black hole in the early universe, not just swallowing everything in its path, but actually amplifying waves of energy around it. This isn't science fiction, it's a real phenomenon called superradiance, and it could have left behind ripples in space-time that we might still detect today. Here's how it works. When a gravitational wave passes near a rapidly rotating black hole, something extraordinary happens. Instead of just being absorbed, some of the wave's energy gets boosted by the black hole's spin, like a surfer catching a perfect wave and riding it to greater heights. This amplified wave then carries away a bit of the black hole's rotational energy, slowing it down ever so slightly. In the chaotic early universe, where black holes were likely spinning at incredible speeds, this process could have created a cascade of supercharged gravitational waves, leaving behind a unique fingerprint in the cosmos. What makes this theory so exciting is that these amplified waves wouldn't just fade into the background. They'd carry a distinct signature, a telltale pattern that detectors like LIGO or future observatories might one day spot. Imagine tuning into a cosmic radio and hearing not just static, but echoes of black holes from the dawn of time, their spins imprinted on the fabric of space itself. While superradiance might sound like an obscure quirk of physics, it's a reminder that black holes aren't just cosmic vacuum cleaners. They're dynamic, energy-shaping engines that could have played a starring role in the universe's earliest moments. Whether these amplified ripples are still out there or lost to time, they offer a thrilling possibility that the secrets of the cosmos might be hiding in the spin of ancient black holes. Now, let's shift gears to another fascinating possibility: tensor modes from scalar fields. Picture the early universe not just as a hot, dense soup of particles, but as a dynamic stage where invisible fields played a starring role. One of these fields, known as the inflaton, might have been the hidden architect behind some of the first ripples in space-time. Here's the idea: scalar fields like the inflaton are thought to have driven the rapid expansion of the universe during inflation. But they didn't just stretch space, they also created tiny fluctuations in it. Some of these fluctuations weren't just random bumps, they were tensor perturbations, a fancy way of saying they could have produced gravitational waves. Unlike the more common scalar perturbations, which affect matter and energy, tensor perturbations warp space-time itself, leaving behind ripples that might still echo through the cosmos today. What's intriguing is how this differs from standard inflationary predictions. In the classic picture, gravitational waves are generated by quantum fluctuations in space-time during inflation. But if scalar fields were the main source, the ripples would carry a unique signature, a different pattern in their strength and frequency. This could mean that future detectors, like next-generation observatories, might not just confirm inflation, but also reveal which fields were pulling the strings in those first moments. Think of it like listening to a symphony. Standard inflation gives us one set of notes, while scalar fields could add a whole new layer of harmony. If we're lucky, the universe's oldest gravitational waves might still be playing this cosmic tune, waiting for us to decode it. Whether these ripples came from the inflaton or another scalar field, they're a reminder that the early universe was far more complex and musical than we ever imagined. Now, let's turn our attention to one of the universe's greatest mysteries: why there's so much more matter than antimatter. This imbalance, known as baryogenesis, might have left its mark not just in the particles around us, but in the very fabric of space-time. Here's how it could work. In the early universe, matter and antimatter should have been created in equal amounts, annihilating each other and leaving behind nothing but energy. But somehow, matter won out. The processes that tip the scales, whether through particle collisions, exotic decays, or phase transitions, were likely violent enough to send shockwaves through space-time itself. These gravitational ripples would carry the fingerprints of those chaotic moments, offering clues about how matter came to dominate. What makes this idea so compelling is the connection between particle physics and gravity. If baryogenesis involved high-energy events like the decay of heavy particles or the collapse of cosmic defects, those processes could have generated gravitational waves with unique frequencies. Future detectors might one day pick up these signals, giving us a direct window into the universe's first moments, and perhaps solving the matter-antimatter puzzle once and for all. Imagine it like finding a hidden message in an old recording. The static might seem random, but buried within it could be the echoes of the universe's most pivotal battle. Whether these ripples come from particle collisions or something even stranger, they remind us that the cosmos has always been a stage for drama, and we're just beginning to listen in. Now, let's venture into something even more mind-bending: phantom energy. Picture this. What if the universe's expansion doesn't just slow down or level off, but instead accelerates so violently that it rips space-time apart? That's the terrifying idea behind phantom energy, a hypothetical form of dark energy with a twist. Unlike ordinary dark energy, which pushes the cosmos apart at a steady pace, phantom energy grows stronger over time. The result, a cosmic doomsday called the Big Rip. Here's how it could create space-time ripples. As phantom energy intensifies, it wouldn't just stretch the universe, it would shred it. Galaxies, stars, even atoms would be torn apart in a final, catastrophic expansion. But before that grim finale, the extreme gravitational forces involved might generate violent waves in space-time itself. These ripples would be unlike anything from black hole mergers or cosmic inflation. They'd be the death throes of the universe, echoing across the fabric of reality. What's fascinating is that these waves could carry clues about phantom energy's nature. If future detectors pick up strange, high-frequency gravitational signals with no known source, they might be hearing the early tremors of the Big Rip. It's a chilling thought, but also a thrilling one, because even in destruction, the universe could leave behind a message. And if we're listening closely, we might just catch it before the final curtain falls. Up next, we'll explore a different kind of chaos, a primordial soup of neutron stars colliding in the early universe, and how their crashes could have sent ripples through time. Now, let's turn the clock back even further, to a time when the universe was so dense and hot it resembled a bubbling cosmic soup. Picture this: not long after the Big Bang, the entire cosmos was packed with unimaginably dense matter, a seething sea of particles where conditions were so extreme that neutron star-like objects could form and collide in rapid succession. These weren't the neutron stars we know today, but their primordial ancestors, born in the universe's fiery infancy. Every collision between these ultra-dense objects would have sent shockwaves rippling through space-time, creating gravitational waves far more powerful than anything we detect now. Think of it like dropping boulders into a pond, except the pond is the fabric of reality itself, and the boulders are chunks of matter so dense, a teaspoonful would weigh billions of tons. These waves would carry secrets about the universe's earliest moments, frozen in time. What makes this even more fascinating is the connection to quark-gluon plasma, a state of matter so exotic it hasn't existed naturally since those first microseconds after the Big Bang. In particle colliders like the Large Hadron Collider, scientists recreate this plasma by smashing atoms together at nearly light speed. The primordial neutron star collisions might have done something similar on a cosmic scale, churning the universe into a quark-gluon soup and leaving behind gravitational echoes of that chaos. If we could detect these ancient ripples, they'd give us a front-row seat to the universe's most violent nursery, where matter itself was forged in collisions of unimaginable force. Up next, we'll explore a universe that spins literally as we dive into Kurt Gödel's rotating cosmos and its potential gravitational wave fingerprints. Now, imagine a universe that doesn't just expand, it spins. This isn't science fiction. It's a serious idea proposed by one of the greatest minds of the 20th century, Kurt Gödel. Best known for his work in mathematics and logic, Gödel also tackled Einstein's equations of general relativity and found something astonishing, a solution that describes a universe rotating as a whole. In Gödel's model, the cosmos isn't static or simply expanding, it's whirling through space-time like a colossal top. If this were true, the rotation would warp the fabric of reality itself, creating subtle but detectable distortions in gravitational waves. Picture ripples on a pond, but instead of being caused by a single splash, they're shaped by the entire pond spinning beneath them. These waves wouldn't look like the ones from black hole mergers or cosmic strings. They'd carry a unique signature, a kind of cosmic fingerprint left by a universe in motion. What's wild is that this idea isn't just a mathematical curiosity. If the universe really does rotate, even slightly, it could explain why some galaxies seem to align in unexpected ways, a puzzle astronomers call large-scale anisotropy. And here's where gravitational wave detectors come in. Future observatories like the Laser Interferometer Space Antenna might be sensitive enough to spot the faint whispers of this universal spin, if it exists. Gödel's rotating universe challenges our basic assumptions about reality. It suggests that the cosmos might not be as uniform or as straightforward as we think. And if gravitational waves ever reveal evidence of this spin, it would rewrite our understanding of the universe's very structure. Up next, we'll take a playful but thought-provoking turn. What if space-time ripples aren't natural at all, but glitches in a cosmic simulation? Now, let's take a step into the realm of the truly mind-bending. What if the ripples in space-time we've been detecting aren't natural phenomena at all, but something far stranger, glitches in a cosmic simulation? This idea isn't just science fiction. It's a serious hypothesis put forward by philosopher Nick Bostrom. He suggests that if advanced civilizations could run universe-scale simulations, there's a good chance we might be living inside one. Think of it like a video game. Even the most advanced software has tiny bugs or imperfections, unexpected flickers, lag, or textures that don't quite load right. If our universe is a simulation, gravitational waves could be the equivalent of those glitches, tiny errors in the code of reality itself. These ripples might not follow the usual rules of physics because, well, they weren't part of the original programming. Here's where it gets even wilder. If we ever detect gravitational waves with patterns that don't match any known astrophysical source, no black holes, no cosmic strings, no spinning universes, it could be a hint that something deeper is going on. Maybe these anomalies are artifacts, leftover traces of the simulation's underlying framework. Some scientists have even joked that finding a mathematical signature in gravitational wave data, like a repeating sequence or an unnatural symmetry, could be the ultimate Easter egg from the programmers. Of course, this idea is speculative, to say the least, but it's a fascinating thought experiment that challenges us to question the very nature of reality. If space-time ripples can't be explained by any of the theories we've explored so far, could simulation glitches be the answer? It's a playful possibility, but one that reminds us just how much we still have to learn about the universe or the simulation we call home. And with that, we've reached the end of our journey through 30 incredible theories about the universe's first space-time ripples. From cosmic inflation to colliding bubble universes, from dark matter whispers to simulation glitches, each idea offers a unique window into the mysteries of our cosmos. So tell us which theory resonates with you the most. Drop your thoughts in the comments below, and don't forget to like, subscribe, and hit the notification bell so you never miss an adventure into the unknown. Until next time, keep looking up and keep questioning everything. As we wrap up this cosmic journey, one thing becomes clear. the universe is far stranger and more mysterious than we could have ever imagined. From the explosive predictions of inflationary cosmology to the mind-bending possibility of simulation glitches, each of these 30 theories paints a radically different picture of how space-time's first ripples might have formed. Some are grounded in rigorous math, while others push the boundaries of imagination, but all of them share one thing in common. They challenge us to rethink everything we thought we knew about reality. What's truly exciting is that we're on the verge of uncovering answers. With next-generation detectors and bold new experiments, we might soon find clues hidden in the faintest whispers of gravitational waves. Will inflation's quantum fluctuations be confirmed? Could cosmic strings or colliding universes leave their mark in the data? Or will we stumble upon something entirely unexpected, a signature that forces us to rewrite the rules? That's the beauty of science. It's a never-ending adventure. So now it's your turn. Which of these theories sparks your curiosity the most? Do you think the truth lies in the math of black holes, the chaos of dark matter, or even the code of a simulated cosmos? Drop your thoughts in the comments below. We'd love to hear which idea captures your imagination. And if you enjoyed this dive into the unknown, don't forget to like, subscribe, and hit the notification bell so you never miss another journey to the edges of our understanding. Until next time, keep wondering, keep questioning, and keep looking up. The universe still has so many secrets left to share.